You think you know what an atom looks like because you've seen the picture 1,000 times. A tiny nucleus in the middle like a little ball, electrons looping around it like planets around the sun. Clean, simple, easy to draw. Snorts, that diagram is everywhere. Textbooks, posters, museum models hanging from ceilings with little balls on wires spinning in neat circles. But here's the problem. That picture is wrong. Not a little simplified wrong. Not close enough wrong. Completely, fundamentally wrong, in a way that should make you suspicious of everything else you learned the same way. The atom is not a miniature solar system. Electrons are not little planets. And if you try to understand what's really happening inside an atom using that image, you're going to fail because you'll ask the wrong questions and then wonder why reality won't answer you. So let's start over and talk about what's actually inside an atom. And I'm warning you now, your brain won't like it, because the truth is so anti-common sense that your intuition will fight it at every step. We'll start with hydrogen, the simple atom, one proton, one electron. That's it, the one everyone uses because it's supposed to be easy. You imagine a proton sitting in the center and the electron somewhere out there orbiting. Then you ask the most natural question in the world, where exactly is the electron right now? You want to say, it's over there, on the left side, moving around the nucleus. And that's where the classical picture dies, because the electron is not over there. The electron does not have a definite position before you measure it. Not because our tools aren't good enough, not because we're missing some hidden detail, but because the electron itself doesn't have a single location until measurement forces an outcome. This isn't philosophy. This is the rule the math writes down, and experiments confirm again and again. If you want to understand atoms, you have to accept this first. The world at this scale does not behave like objects you can point at and track like a baseball. Before measurement, the electron exists in what we call a superposition. It's not here or there. It's described by a spread out set of possibilities. Multiple might be here outcomes at once. But don't misunderstand what that means. You might think, okay, so it's a cloud, like the electron is smeared out through space like fog. No, that's still the wrong instinct. When you actually detect an electron, you don't detect a fog. You detect a point, a localized hit, a dot on a screen, a click in a detector. So what's spread out isn't the electron as a little substance. What's spread out is the probability of finding it in different places. That probability is encoded in something called the wave function. In some regions, the wave function is large. High chance you'll find the electron there if you look. In other regions, it's small. Low chance. In some regions, it is exactly zero, meaning you will never find the electron there, no matter how many times you try. And here's the part that melts your brain. Before you look, the electron isn't hiding in one of the high probability zones like a thief behind a curtain. It isn't secretly located somewhere, and you just don't know where. It genuinely doesn't have a location. The wave function isn't a map of ignorance. The wave function is the full description of what the electron is doing. That is why classical questions break. Where is it? Assumes the electron must have a position. Quantum mechanics says, position is not a property the electron carries around like a tag. Position becomes definite only when measurement forces a definite outcome out of the menu of possibilities. If you try to force the atom back into a neat little picture, tiny planet, tiny orbit, you'll spend your whole life confused because the atom refuses to be visualized that way. Now let's talk about orbits, because this is where the solar system analogy doesn't just wobble, it collapses. Suppose the electron really did circle the nucleus like a planet. Then it would be accelerating, because anything moving in a circle is accelerating even if the speed stays constant. Accelerating charges radiate energy. They emit light. That's basic electromagnetism. So an orbiting electron would constantly lose energy, radiate it away, and spiral inward. The orbit would shrink. The electron would plunge closer and closer to the nucleus until crash. The atom collapses. Run the numbers and it happens ridiculously fast, around 10⁻11 seconds. If that picture were true, every atom in the universe would self-destruct instantly. But atoms are stable, so the electron can't be orbiting. Fine, you say. Then maybe it's sitting still, pinned in place by attraction. Also wrong, because if it were stationary, You'd know both its position, right there, and its momentum, zero. Quantum mechanics forbids exact position and exact momentum simultaneously. That's the uncertainty principle. Not a limitation of measurement, but a property of nature. Fix position too precisely, momentum becomes uncertain. Fix momentum too precisely, position becomes uncertain. So the electron is not orbiting and not sitting still. So what is it doing? In the classical sense, nothing. It exists as a wave function, a mathematical description of probabilities with allowed shapes and energies. Those allowed shapes are called orbitals. And an orbital is not a path. It's not a little track the electron runs on. It's a probability structure, regions where the electron is likely to appear if you measure it. The ground state of hydrogen is spherical, highest probability near the nucleus, falling off with distance. Higher energy orbitals have weirder geometry, dumbbells, donuts, multi-lobed structures. Again, not objects, not stuff, but probability patterns. And when the electron changes energy, it doesn't glide smoothly from one orbital to another like a satellite changing altitude. It jumps instantaneously, a quantum leap. One moment the wave function has one shape, the next moment it has another. No in-between, no mechanism you can point to. The math predicts it. Experiments confirm it. Nature doesn't explain it in the comforting way you want. Now let's make it even more unsettling and ask, what is the electron itself? You want it to be a tiny ball with mass and charge, a particle, a thing. Except electrons also behave like waves. They diffract. They interfere with themselves. They spread out and recombine. Classic wave behavior. So which is it, wave or particle? Neither. It's a quantum object, something, that has no clean classical analogy. When you aren't measuring, it is described by a wave function that evolves smoothly and can interfere like a wave. But when you measure it, when you actually detect it, you always get a localized event, never a smeared out wave. The act of measurement collapses. The wave function, the spread out probability pattern, becomes one definite outcome, here and not there. And nobody can tell you exactly how that happens. Nobody agrees on what counts as a measurement. Nobody can point to where the wave function goes. This is the measurement problem. And it has haunted physics for nearly a century. There are interpretations, many worlds, pilot waves, objective collapse, but those are interpretations, not a universally accepted mechanism. The brutal fact is, the math works. The predictions match experiments with insane precision, but our human desire for a neat picture of what's really happening hits a wall. Now add more electrons and the weirdness becomes structural, not just philosophical. Helium has 2 electrons. Carbon has 6, iron has 26. They're not little balls flying around like bees. They're quantum states, wave functions, occupying allowed patterns around the nucleus. And they are identical in the deepest sense. Not just look the same, fundamentally identical. If you swap 2 electrons, the total wave function changes sign. That fact isn't decoration. It is the engine behind one of the most important rules in nature, the Pauli exclusion principle. No 2 electrons can occupy the same quantum state. That one rule is why matter is solid, why atoms have structure, why chemistry happens, why complex life is possible. Without it, all electrons would drop into the lowest energy state, every atom would behave the same, and the universe, wabiu, would be chemically dead. Why does swapping identical particles flip a sign? We don't know. It's simply what nature does. The math demands it. Experiments agree. That's it. You might think the nucleus is the simple part. Protons and neutrons packed together like little balls stuck in a cluster. Wrong again. Protons and neutrons are not fundamental. They're made of quarks. 3 quarks bound by the strong force carried by gluons. But even that picture of quarks as tiny marbles inside a bag is too classical. The proton is a quantum-bound state, a stable pattern of interacting fields with quarks and gluons fluctuating and exchanging constantly. And here's a fact that should rewrite your intuition about mass. Most of the proton's mass doesn't come from the quarks themselves. Quarks are nearly massless compared to the proton. The mass comes largely from the energy of the gluon field binding the system together. Energy equals mass. So when you ask what's inside a proton, the honest answer is energy arranged in a stable pattern, not little hard pieces of matter. In the nucleus, protons and neutrons are held together by residual strong interactions, often described as exchange effects involving particles like pions. But pions are also quark-based excitations. It's quantum fields all the way down. Now step back and ask again, what's inside an atom? Not planets, not orbits, not balls, not stuff in the comforting tactile sense. What's inside an atom is fields, quantum fields. The citron field, the quark field, the gluon field, the electromagnetic field. These fields fill space. They are everywhere, all the time. When we say an electron is in the atom, what we really mean is that the electron field has an excitation bound near the nucleus, shaped by the allowed quantum states. The atom is not a thing the way a rock is a thing. It is a stable configuration of interacting field excitations held together by forces that are themselves mediated by other excitations. There are no solid objects at the bottom. There is no final stuff. There are patterns, equations, symmetries, conservation laws, and somehow those produce everything you experience as physical reality. And that should bother you, because your mind wants something solid at the foundation, something you can point to and say, that is what it's made of. But when you chase the atom down to its core, you don't find solid pieces. You find math, fields defined over space and time, assigning values everywhere, evolving according to differential equations, snorts numbers that sometimes behave like localized particles when you measure them and like spread out wave functions when you don't. You've heard the atom is mostly empty space, but even that is misleading, because empty does not mean nothing. The vacuum is alive with quantum activity. Fields still exist there, virtual fluctuations still occur, and the electron's wave function extends through the atomic region as a non-zero amplitude. When you push on a table, you aren't feeling tiny billiard balls smashing into each other. You are feeling electromagnetic repulsion between electron configurations and the exclusion principle preventing identical electrons from occupying the same state. It feels solid because the rules are strict, not because matter is made of little hard pellets. Scale makes it worse. The nucleus is about 100,000 times smaller than the atom. If the nucleus were the size of a marble, the atom would be the size of a stadium. Yet the electron, as far as we can tell, has no size at all. Experiment after experiment is consistent with it being point-like, a point-like entity occupying a vast atomic region through probability. Does that make intuitive sense? Of course not. Nature doesn't care. Then there's spin. Electrons have intrinsic angular momentum, yet they cannot be literally spinning like a top because a point has no extent to rotate. Still, the property exists, quantized, so you only ever measure discrete outcomes. Energy levels are quantized too. The electron can only have specific energies because the wave function must fit into allowed standing wave patterns around the nucleus, like harmonics on a string. When it changes levels, it emits or absorbs a photon with exactly the energy difference, producing precise spectral lines. We can calculate those lines to absurd precision and experiments match them. The theory works, but your intuition never gets a neat picture. And when you try to look inside the atom, you run into another fundamental wall. To resolve small scales, you need short wavelengths, which means high energy, which means you disturb the system. There is no passive observation in the quantum world. Measurement doesn't merely reveal a pre-existing fact. It forces a definite outcome from a range of possibilities. Before measurement, a wave function, a superposition of potentialities. After measurement, one actual result. So what's really inside an atom? Not little balls, not orbits, not mechanical trajectories. What's inside is a mathematical structure, a wave function governed by the Schrödinger equation, built from quantum fields whose excitations sometimes look like particles when you measure them. You can't truly picture it because the wave function isn't a physical wave in space. It's an object in an abstract mathematical space, encoding complex probability amplitudes. And yet, from this abstract machinery emerges everything: chemistry, biology, your body, your thoughts. That is what's inside an atom. Not stuff, but patterns in fields, written in equations, pure, abstract, beautiful, and to human intuition, almost incomprehensible math.